This question is about using a digital balance to investigate the force on a wire placed in a magnetic field when there is an electric current in the wire. A student carries out the procedure shown in Figure 1 and Figure 2. A meter ruler is pivoted at the 1 centimeter mark and a prism is placed on a digital balance. The free end of the ruler is raised and the balance is turned on and then set to 0, as shown in Figure 1. So you can see we have Figure 1 there with the ruler attached at a clamp, and then the prism will be used to support the ruler above the digital balance. The ruler is then supported by the prism with the apex of the prism at the 30 centimeter mark, as shown in Figure 2. The height of the pivot is adjusted so that the ruler is horizontal, and there we can see that prism supporting the ruler. To deduce the mass of the ruler, state one assumption you make. So we're going to need to apply the principle of moments to this question. Let's just look back at the data that we're given. So in Figure 2, we can see that at this point on the ruler, the reading is 214.66 grams. So if we calculate the force needed to cause that mass reading, so we've calculated the force at that point. Now we know that the weight of the ruler is going to be acting at its center of mass. But the point of application on the scales, as we can see, is closer to the pivot. So the weight experienced by the mass balance will be greater than the weight of the ruler. So let's write our information into the answer space. So I've said here that the clockwise moment must be equal to the anti-clockwise moment, and if that happens, then the ruler will be in rotational equilibrium. Now we can say that the weight multiplied by 0.5 meters, which is where we can say the weight applies, is equal to the force acting on the balance multiplied by the distance of that balance from the pivot, because that's where that force on the balance is applied. Now in saying this, we're saying that the moment is calculated as the force multiplied by the perpendicular distance from the pivot. Now we can see that that point of application is at the 30 centimeter mark, but what we need to be careful of is that the pivot is also at the 1 centimeter mark, which will mean that the mass balance is at 29 centimeters, and actually the center of mass is 49 centimeters from the pivot. So we need to make some edits there. So you can see I've changed the distance of the center of mass to 0.49 meters from the pivot, but we also need to add to the anti-clockwise moment because some of that ruler is on the other side of the pivot. Granted, it's only a small amount because it's 1 centimeter of the ruler, but it still contributes to that anti-clockwise moment. And because it's only a centimeter of the meter ruler that's on the left-hand side of the pivot, then we can say it has a weight which is equal to 100th of the weight of the ruler. Now we're trying to calculate the mass of the ruler, so let's rearrange to make the weight the subject. And then substitute in the rest of our values. So that gives us a weight of 1.247 newtons, but don't forget that we're trying to find the mass, so we need to divide this value by 9.81 newtons per kilogram. So that gives us 0.127 kilograms, which we need to write in grams, so that will be 127 grams. Now the assumption that we've made all the way through this question, especially when talking about the 1 centimeter part of the ruler that's on the left-hand side of the pivot, is that that mass of the ruler is uniformly distributed, that there isn't some area of the ruler which is denser than another area, because that would affect where the center of gravity is on the ruler, and therefore where the weight is applied. So in terms of marks for this question, you'd get 1 mark for applying the principle of moments, another mark for correctly calculating 127 grams, and a 3rd mark for correctly stating an assumption. So 3 marks there. The student attaches a uniform wire to the upper edge of the ruler as shown in Figure 3. The ends of the wire are connected to terminal blocks P and Q, which are fixed firmly to the bench. A power supply and an ammeter are connected between P and Q. These modifications cause the balance reading to increase slightly. A horizontal uniform magnetic field is applied, perpendicular to the wire, between the 85 cm and 90 cm marks, as shown in the close-up diagram in Figure 3. So we can see Figure 3 there, with a shaded area representing where the magnetic field is applied, with a width of 5 cm. The balance reading M is recorded for increasing values of current I. A graph of these data is shown in Figure 4. So we can see Figure 4 there, with mass on the y-axis and current on the x-axis, and there's a straight line graph there with a constant negative gradient. State and explain the direction of the horizontal uniform magnetic field. Now if we go back to the diagram, the first thing that you'll notice is that the position of the mass balance hasn't changed, but its reading has increased. Now this could be due to the weight of the wire, so we don't have the full picture here, but let's look at the graph. Now on this graph you can see that as you increase the current reading, the mass reading goes down. So the more current we put through the wire, the less force is applied to the mass balance, which must mean that the magnetic force is acting to lift the meter stick. So the first thing that we can say is that the force is acting upwards, and that will gain us our first mark. Now the pieces of information that we need to work out which way the field is directed are the direction of the currents and Fleming's left-hand rule. So let's just work out which way the current is going. You can see in this diagram that the larger line on the variable power supply is on the left-hand side. So the positive current is moving clockwise around the circuit and therefore from left to right in the wire at the meter stick. And stating that will get us our second mark. And the last thing to do is apply Fleming's left-hand rule to try and work out which way the field is acting. So using Fleming's left-hand rule, we know that the middle finger represents the current. So if we line that up from left to right, the force, which is the thumb, is acting upwards. So when you line those things up, we can see that our index finger goes directly into the page, perpendicular to the page surface. So your last mark will be for saying that the magnetic field is acting into the page. And that would be your third mark. So 3 marks there. It can be shown that B, the magnitude of the magnetic flux density of the horizontal uniform magnetic field, is given by B equals sigma over 3L, where sigma is the change in force acting on the prism per unit current in the wire, and L is the length of the region where the magnetic field cuts through the wire. Determine B. Now a quantity of interest here is sigma, which is the force per unit current. Now the force acting on the prism is equal to the mass reading multiplied by the gravitational field strength. So we can make a substitution. Now the reason I know that this is going to be a constant value is because the gradient of the graph is constant. So we can rewrite this slightly differently. Now the reason I've written this as delta m divided by delta I is because delta m divided by delta I is going to be the gradient of this graph, although they've used a capital M here. So to find the value of sigma, all we need to do is find the gradient of the graph and multiply it by the gravitational field strength, which is just 9.81 newtons per kilogram. We said before that L is equal to 5 centimeters. So let's go back to the graph. Now what we can do is take this triangle and divide the height of the triangle by the base width of the triangle to find the gradient, i.e. delta m divided by delta I. So let's do that now. So we have a change of -1 grams because it's going downhill, or -10 to the -3 kilograms. We'll now have a positive value for delta I. So the change in current is going to be 3.55 amps. So we find the gradient by dividing the two values. So we end up with -2.817 times 10 to the -4 kilograms per amp. So let's write that in the answer space. So we need to multiply that by G to find sigma, but we might as well divide it by 3L as well to get B. So we end up with a value of minus 0.0184 Tesla, but you'll notice that B is the magnitude of the magnetic flux density of the field, so really we don't need to worry about the minus. So in terms of marks, your first mark will be for finding the gradient of the graph using a triangle with a bigger base width than 2 amps. Your second mark will be for the use of G, 9.81 newtons per kilogram, and your third mark will be for correctly calculating the magnitude. So 3 marks there. The experiment is repeated with the ruler pivoted at the 99 centimeter mark. Nothing else has changed from figure 3. This arrangement is shown in figure 5. You can see we've got that horizontal uniform magnetic field. The crosses on that grey box represent that the field is going into the page. Tick one box in row 1 and one box in row 2 of table 1 to identify the effect, if any, on the magnitude of the forces acting on the apparatus as a certain current is passed through the wire. Tick one box in row 3 and one box in row 4 of table 1 to identify the effect, if any, on the graph produced for this modified experiment compared with the graph in figure 4. So we've got that table there with 4 quantities and then columns to show whether they're reduced, increased, or if there's no effect at all. So let's first of all talk about the force acting on the current carrying wire. Now the only thing that's changed here is the position of the pivots. The magnitude of the magnetic field doesn't change, and neither does the current. As you can see, nothing else has changed from figure 3. So based on the equation F equals BIL, we can see that if there are no other changes, then F will be unaffected. So for row 1, there will be no effect. Looking at the force acting on the prism due to the pivoted ruler, you can see that the prism is moved from being 29 centimeters from the pivot to being 69 centimeters from the pivot. So the force caused by the weight of the ruler will be larger. So the force exerted due to the weight of the ruler will be smaller, because in terms of clockwise and anti-clockwise moments, while the ruler exerts the same anti-clockwise moment as it did clockwise moment in the previous part of the question, the perpendicular distance of the balance is greater, so its force must be smaller. Remember that in a moment, force and distance are inversely proportional, as the force and distance are multiplied together. Now you could argue that the effect of the magnetic field lifting the ruler off of the mass balance is going to be smaller, and therefore there's more force pushing down on the mass balance, but the factor by which that magnetic force has decreased is going to be larger, so the force acting on the prism due to the pivoted ruler is going to be reduced. Looking at the gradient of the graph, remember that this gradient is the change in mass divided by the change in current. This is equal to delta M over delta I, and because of the change in position of not only the mass balance and the prism, but the magnetic field where the force is applied, because the magnetic field is closer to the pivot, a given change in current will cause delta M to be lower, so this will be reduced. Looking at the vertical intercept of the graph, whilst we can't see it on this graph, this will be the point at which there is no current in the wire, and therefore there will be no magnetic field contribution. Now, because the force exerted on the prism is smaller, as we said in point 2, the mass reading when the current is 0 and there is no magnetic field around the wire must also be lower. So in terms of marks for this question, your first 2 marks will be for getting row 1 and row 2 correct, and your third mark will be for getting rows 3 and 4 correct. So 3 marks there. Figure 6 shows the balance being used to measure the forces between 2 wires. The connections joining these wires to the power supply are not shown. The pan of the balance moves a negligible amount during use, and it supports a straight conducting wire X of horizontal length L. Terminal blocks are used to connect X into the circuit. The weight of these does not affect the balance reading. A second conducting wire Y is firmly supported at distance D above X. Show, by adding detail to figure 6, the wire connections that complete the circuit. The currents in X and Y must have the same magnitude and be in the directions indicated. So you can see in figure 6, we've got the power supply with the ammeter, and then the two wires at a distance d from each other above the mass balance. So we need to make sure that the currents in these two wires are the same at all times. So to do that, we should make a series circuit. So here's my series circuit. It does cross over, but we need to do that in order to make the currents flow in the same direction, i.e. from left to right. So if we indicate that current direction, your first mark will be for creating a circuit so that those currents move in the same direction. Now it could be that you've created a non-series circuit, i.e. a parallel circuit, and still got that mark, but to get the second mark it needs to be a series circuit so that the currents remain the same. So 2 marks there. The vertical force F on wire X due to the magnetic field produced by wire Y is given by F equals Ki squared L over D, where K is a constant, D is the perpendicular distance between X and Y, I is the current in the wires, and L is the horizontal length of wire X. A student wants to measure K using the arrangement in figure 6. The student is told that the following restrictions must apply. L is fixed, I must not exceed 5 amps, the result for K must be obtained using a graphical method, and the experimental procedure must involve only one independent variable. Explain what the student could do to find K. Now the first thing that we want to do is rearrange the equation into a straight line format, where we're varying the value of I squared and taking readings of F. Now F is affected by the mass balance reading, so we can adjust this. So we can see that this fits a straight line format. Now there wouldn't be a plus C here because this graph passes through the origin, but the mass readings will be on the y-axis and the current squared readings will be on the x-axis. So current is our independent variable and mass is our dependent variable, and our first mark is going to be for stating that. So that would be your first mark. You get another mark for saying that the force values are just the mass balance reading values multiplied by the gravitational field strength. Your next mark will be for saying what the control variables are, i.e. the other values in the gradient expression in the equation that we rearranged. So the things to keep the same here will be L and D. We know that K and G will remain the same anyway because K is a constant and G won't change. We get another mark for saying that these are just lengths, so they can be easily measured. It's worth noting here that there's a maximum of 3 marks available for the strategy used. Now we're going to move on to analysis now, which has 2 marks available. The first thing to say here would be to plot a graph with mass on the y-axis and current squared on the x-axis. Be careful not to get these mixed around. We want the mass reading to be the dependent variable and I squared to be the independent variable. The last thing to say here is what the gradient of this graph represents. So we can rearrange this to make K the subject. Now technically speaking, there are other ways to do this. For example, you could put I squared L on the x-axis, which would mean that your gradient is equal to K over dg, and so on, but this method is fine. So those are your 2 analysis marks, bringing us to a total of 5 marks for this question. This question is about an experiment with a retractable steel tape measure. The tape measure is placed at the edge of the bench, and about 1 meter of the steel tape is extended so that it hangs over the bench. The tape is then locked in this position to stop it from retracting. A student measures the dimensions x and y, the horizontal and vertical displacements of the free end of the tape, as shown in figure 7. So we've got figure 7 here with a retractable tape measure there that hangs over the edge of the desk, and then the floor underneath. Describe a suitable procedure the student could use to measure y. You may add detail to figure 7 to illustrate your answer. So let's go back to figure 7. And we can see that y is just the vertical distance between the bottom of the tape measure and the top. So the first thing to do is use a piece of apparatus to show horizontally where the top of that distance y will be, and we're going to use something like a meter stick for this. So drawing this can be part of our answer. We just need to make sure that we label that it's a meter stick. Now drawing this alone wouldn't be enough to get our first mark. The first mark will be obtained for using a second meter stick, which is held vertical, to measure how far below the first meter stick the end of the tape measure is. And there's our second meter stick. And drawing this will give you your first mark. So let's go back to the answer space. So I've put C diagram there to show that there's something illustrated on there. For our second mark, we need to say that that second ruler needs to be made vertical using something like a set square. And it's the mention of this accuracy measure that will get you your second mark. So 2 marks there. By changing the extension of the tape, the student obtains further values of x and y. These data are shown in Table 2. So we have Table 2 with a range of x and y values. Suggests why the student chose to make all measurements of x greater than 70 centimeters. So the thing to remember here is that there's going to be a particular absolute uncertainty in our length readings. And that's because we're judging them by eye, we're using a meter stick or a ruler with a certain scale, with divisions that only go down to a certain amount. But we find the percentage uncertainty in our length readings by dividing that absolute uncertainty by the reading itself, which means that the larger the reading is, the smaller the percentage uncertainty is. So mentioning percentage uncertainty is going to be what gets us our mark. So you don't need to go into detail on how the percentage uncertainty is calculated, but you do need to mention percentage uncertainty to get this mark. So just the 1 mark there. The data from the experiment suggests that y equals a times x to the power of n, where n is an integer and a is a constant. These data are used to plot the graph in Figure 8. Determine n using Figure 8. So let's go to the graph. So we can see Figure 8 here with a range of points plotted on a y-axis scale which ranges from 1.8 down to 0.7. The origin 0, 0 isn't present, but we don't need that because we're only finding the gradients of the graph. Let's go back to the answer space first. Now, first of all, we need to work out what the gradient that graph is going to represent. So let's take logs of both sides of this equation first of all. Now we can expand the log on the right-hand side to separate those variables from each other. Now the log rules that we've used are as follows. Log of AB is equal to log A plus log B. And log of A to the power of B is equal to B times log of A. So now, based on what our x and y values are on the graph, this starts to look a lot more like a straight line graph equation. So rearranging this slightly, we can then apply the straight line graph equation. So we can also see that the y-intercept of this graph, or c, is going to be equal to log a. So the gradient of this graph will represent n. So let's plot a line of best fit and find the gradient. So we now have a suitable line of best fit through the graph. Let's make this into a big triangle so that we can find the change in y value and the change in the x value. So I measure a change in the y value of 1.79 minus 0.73. And that gives us a value of 1.06. Now by y here, I mean the y-axis, not the actual y values that are measured in the experiments. If we do the same for the x value, we've got a change in x of 2.125 minus 1.85, which gives us a value of 0.275. So let's divide these in the answer space to get our gradient. So we end up with a value of 3.85, which doesn't have a unit. Now we're saying here that n is an integer, so we need to round this. So it rounds to 4. So let's put 4 in the answer space. Now in terms of marks for this question, you get 1 mark for drawing the line of best fit. You get another mark for correctly calculating the gradient, and a 3rd mark for getting the correct answer, which is rounded to the nearest integer, so 4. So 3 marks there. Explain how the numerical value of A can be obtained from Figure 8. So the first thing to say here, as I mentioned before, is that the value of log A is going to be the y-intercept. And that will get you your first mark. The problem is that our graph doesn't pass through the origin, so we can't just use the value where it passes through our y-axis. So what we need to do is substitute some values into our equation. So let's choose a point on our line and substitute in the values. So let's choose this point here. And this point on the line has a value of 1.31. So let's write that in the answer space. So let's substitute that into the equation. Now what we need to do is rearrange this equation to make A the subject. Now bear in mind that this is an explain question, and our answer currently doesn't have a lot of explaining, just calculation. So we need to explain what we're doing at different steps. So your second mark will be for explaining that you need to select certain values of log x and log y and substitute them into an equation. What we should then do is give a general expression on how to find A, and that will gain you your third mark. It doesn't matter which values of x and y you choose, as long as you can explain what you're doing. So 3 marks there. Estimate the order of magnitude of A. You should use data for x and y from any one row in Table 2 on page 11. Give your answer with an appropriate unit. So let's select a row from the table. Let's go for one in the middle. So x is equal to 105.1 and y is equal to 24.3. So rearranging the equation, we can say that A is equal to y over x to the n. More importantly, as we saw before, A is equal to 10 to the power of log y minus n log x. So all we need to do now is substitute in our values. And we end up with a value of 1.99 times 10 to the minus 7, which is going to be in centimeters to the minus 3. Now it doesn't matter whether we use 4 or 3.85 for the value of n. I've used 4 here so that we know that our value is definitely going to be in centimeters to a minus integer value, i.e. minus 3. But I'll just indicate here y is centimeters to the minus 3. So we're dividing a value in centimeters by a value in centimeters to the power of 4. So that will give us a value in centimeters to the minus 3. Now we only need the order of magnitude of A. If you were to use n equals 3.85, you get a value of 4 times 10 to the minus 7. You'd get a value of 4 times 10 to the minus 7. So your order of magnitude of A would still be the same. Now in terms of marks for this question, your first mark will be for evaluating A correctly and to a minimum of 2 significant figures. Your second mark will be for getting the correct power of 10, and your third mark will be for getting the correct units. So 3 marks there. This question is about an experiment to estimate absolute zero. Figures 9a to 9d show the stages in the procedure carried out by a student. An empty flask fitted with a tube and an open valve is placed in water bath H containing hot water. The air inside the flask is allowed to come into thermal equilibrium with the water. The valve is then closed, trapping a certain volume of air as shown in figure 9a. So we have figure 9a there with the beaker of water as described. This is hot water and the valve is closed. The flask is inverted and placed in water bath C, in which the water is at room temperature. The air inside the flask is again allowed to come into thermal equilibrium with the water, as shown in figure 9b. So you can see figure 9b there with the inverted flask with the water now at room temperature. The valve is opened and some water enters the flask, as shown in figure 9c. So as described in figure 9c, the water is now moved up through the valve and the volume of air is smaller. That will be useful later. The depth of the inverted flask is adjusted until the level of water inside the flask is the same as the level in the water bath. The valve is then closed, trapping the air and the water inside the flask, as shown in figure 9d. So in figure 9d, you can see that the flask has been raised up until the water levels are the same. Explain why the volume of the air in the flask in figure 9c is less than the volume of the air in the flask in figure 9d. So let's compare 9c and 9d. You can see first of all, in 9c, when the water is allowed to enter the flask, the air is compressed. This is because the flask is submerged below the surface of the water, so there is pressure caused by the water above the flask. Comparing this to figure 9D, we can see that the volume is greater, but that's because the pressure is lower. So the relation between pressure and volume that we're going to use is Boyle's law, which we need to write into the answer space. Now this would get you your first mark. I'm just going to write down here what Boyle's law actually says. So Boyle's law states that the pressure of a fixed mass of ideal gas is inversely proportional to its volume at a constant temperature. Now you don't need to write all of that, you just need to say that Boyle's law applies. Now because we're saying that the air in the flask in figure 9C has a lower volume than the air in the flask in figure 9D, we can say that the pressure is greater, as I said before when we looked at the diagram. And that would get you your second mark. You could also talk about the constant temperature, but there's a maximum of 2 marks here. Explain why Charles's law can be applied to compare the air in the flask in figure 9A with the air in the flask in figure 9D. So let's write down Charles's law first of all. So you can see that this law has a very similar style to Boyle's law, but this time we're saying that the volume is proportional to the temperature rather than the pressure is inversely proportional to the volume. And in this law, we're holding pressure constant rather than temperature, like we saw in Boyle's law. Now the 2 marks awarded here will be for saying the 2 things that are held constant, and those are the mass of the gas and the pressure. And those are actually referenced in Charles's law itself. So I've said there that the pressure and the mass of the gas are constant. So that single point will get you both your marks because you're saying the pressure is constant and the mass is constant. Now I've put the 2 ticks at the end because you need to say that they are constant. Mentioning the pressure and the mass alone will not get you either of those marks. You need to say that they are held constant. The flask is removed from water bath C and the valve and stopper are removed. The volume of the water in the flask is V1. The flask is then completely refilled with water and the valve and stopper replaced. The volume of the water now in the flask is V2. The volumes V1 and V2 are shown by the shaded parts in figure 10. So as described there in figure 10, we've got the volumes of water in the flasks. Remember that we are interested in the volumes of gas, but that will be relevant a little bit later on. Explain how V1 and V2 can be determined. In your answer, you should firstly identify a suitable measuring instrument, and secondly, explain a suitable procedure to eliminate possible systematic error. The suitable measuring instrument here is going to be a measuring cylinder. So that's going to be our first mark. So there's your first mark for mentioning volume and a measuring cylinder. So that meets our first bullet point. Our second and third marks will be for explaining the suitable procedure to eliminate possible systematic error. Now the trick with this will be to look at the measuring cylinder at the correct angle, i.e. making sure that your eye is level with the bottom of the meniscus, because we want to avoid what's called parallax error. If you are above or below the bottom of the meniscus, the reading that you obtain for the volume might be too high or too low, depending on where your scale is relative to the liquid. Now for this, you'll get your first mark for mentioning that you need to be level with the bottom of the meniscus, and then mentioning parallax error will be your third mark. I'll just draw a diagram to show what that would look like. So there's my diagram to illustrate that idea. It's always a good idea in the real exam, if you don't feel that you've explained the point well enough, to just draw a quick diagram to help the examiner visualize what you're talking about. But the points I've made in the answer space will get you those 3 marks. Plots points to show the volume V and temperature theta of the air in the flask when the flask is as shown in figure 9A and the flask is as shown in figure 9D. The temperature of the hot water bath is 86 degrees Celsius. Room temperature is 19 degrees C. So we've got V1 is 48 centimeters cubed and V2 is 255 centimeters cubed. Now bear in mind here that those are the volumes of the water, not the volumes of the gas. So let's take a look at figure 9A and 9D. So we can first of all see that there is no water in the flask in figure 9A. It was noted that V2 is equal to 255 centimeters cubed, and you remember that V2 is when the flask is full. So for 9a, we're saying that the volume of gas is going to be 255 centimeters cubed. Let's write that next to our question. So in figure 9a, as I said before, the volume of gas will be at its maximum possible value in that flask. Now let's take a look at figure 9d. So lower down in the question, it's mentioned that when the flask is removed from water bath C, the volume of water in the flask is V1. And that volume is equal to 48 centimeters cubed. Now, if the flask has a total volume of 255 centimeters cubed, then we need to subtract that 48 to get the volume of gas. And that will give us 207 centimeters cubed. So let's annotate the question with this. So it's asking us to plot on figure 1 those points. Let's just write down the coordinates of those points. When the volume of the gas is 255 centimeters cubed, the temperature will be 86 degrees Celsius. Now our x-axis temperature scale is in degrees Celsius, so the coordinates will be 86,255 for figure 9a and 19,207 for figure 9d. Before we plot these points onto the graph, we need to make sure that we have a suitable scale. This scale needs to include the points 207 and 255 on the y-axis, so it's recommended that you start with 200 and go up to 260. Based on the size of the graph that we have, it's recommended that we go up in major intervals of 10 centimeters cubed. So let's do that now. So we can see that I'm starting at 200 and going up to 260. We can now plot our points. Our first point, 19,207, and our second point, 86,255. We will need to draw a line of best fit through these points, but that's in a later question. So in terms of marks for this question, there are 3 available. The first is for having a suitable scale on the y-axis, and then there will be 1 mark available for each of the correctly plotted points. So 3 marks there. Add a best fit line to your graph in figure 11 to show how V should vary with theta according to Charles' law. Now we're saying here that temperature and volume are directly proportional. Now technically the volume is directly proportional to the Kelvin temperature, and on a graph of volume against Kelvin temperature it would pass through the origin. But on a graph of volume against temperature in degrees Celsius, we would still have a straight line graph. So let's plot a straight line through our data. So there's our line of best fit. Your mark will be given if it's a straight line that's thin enough and passes through both of those points. Determine the value of absolute zero in degrees Celsius using your graph in figure 11. So let's go back to our graph. Now we know that absolute zero is going to be the point at which this volume collapses down to nothing. As I said before, volume and Kelvin temperature are directly proportional to each other. So the point at which the volume will be 0, the Kelvin temperature will be at 0. But we're interested in the degrees Celsius temperature at which the volume collapses to nothing. The best thing to do here would be to choose a point on the line and put its coordinates into the straight line equation along with a gradient, which we can calculate. So let's find the gradient first of all. We need to turn this line into a big triangle. So there's our triangle. We've got a change in the y value of 265 minus 200. Our change in the x-axis is going to be 100 minus 10, which is 90 degrees Celsius. So let's calculate the gradient of our graph in the answer space. So we end up with 0.7222. Now the equation of a straight line is y equals mx plus c. So the reason that we want to choose a point on the line is so that we can put this in with the gradient to find a value for c. Once we have the value of c and the value of m, we can make our y value 0 because that's the point at which the line crosses the x-axis, to then find the corresponding value of x. So let's choose a point on our line next. I'm going to go for this point here. Its coordinates are 72, 245. So let's write that in our answer space. So let's put those coordinates into the straight line equation along with the gradient. And then rearrange this to make C the subject. And that gives us a value of 193 centimeters cubed. So just as a fun fact, this would be the volume of gas when the temperature is 0 degrees Celsius. Let's put this y-intercept back into the equation with the gradient, but we'll set our y value to be 0 because we want to find the x-intercept now. Then we'll rearrange to make x the subject. And we end up with a value of minus 267 degrees Celsius. Now this isn't far off from the true value of minus 273, but it's a value that we obtain with the data that we have. Remember that we've only plotted 2 points there. The more points we plot on that graph, the more reliable our data would be, because we get a different value for the gradient and a different value for the y-intercept. But minus 267 degrees Celsius is the appropriate value to put into the answer space. Now, in terms of marks for this question, your first mark will be for calculating vertical intercept or the y-intercept using the correct method. Your second mark will be for using the correct method to find the horizontal intercept or the x-intercept. And your third mark will be for getting an answer within the range of minus 260 degrees Celsius to minus 285 degrees Celsius. So 3 marks there. The other method that you could use is the similar triangles method. If you were to take the big triangle that we made our line into on the graph and then extrapolate that triangle down, we would know how far we need to multiply the height of the triangle to go all the way down to 0, and the width of the triangle would multiply by the same amount, and we could therefore find how far back from 100 degrees that triangle would extend, and therefore the value of absolute 0. That's an alternate method, and that would still get you 3 marks, but the main method is this one here.